Welcome back. I think last session we had seen what is simplified model from exact model, and if the load value is less than or equal to in the order of 4 kilo ohm, we can go for simplified model. We can neglect HOE and we can take HRE approximately which is nearer to 0, therefore we will get the simplified model. Okay. Now maybe the continuation of simplified model only, means again all 4 AC parameters which we already solved, but now what are those if we use simplified model? It is straightforward. You can substitute in the formulae to get wherever you have HRE take 0, wherever you have HOE take 0. That is straightforward, but I want to explain with respect to the circuit. Both will give you the same answer, but I want to explain with respect to the circuit. Okay, now listen, don't write. This is what your amplifier, this is what is your CE amplifier. Okay, now this is what is your load is connected, this is your output, the common is connected to ground. Okay, no need to show. And this is what is your source. Actually we went back to common emitter amplifier. Now we are applying simplified model. Okay, that is fine. See, no CC amplifier, no CC amplifier, no CB amplifier, no CB amplifier, those things are not there. That is the conclusion. Okay, now this is again the AC parameter values if you go for simplified model. Okay, just I can say simplified formulae or simplified derivations. Naturally we went back, that's what I told, we went back. This is your VI and this is what your V0. Okay, that is fine. Now, and if I speak like voltage, current, both at input as well as output, like two-port network, the current which is entering into your amplifier I1 and the current which is what is coming out of or entering into your load is nothing but your IL. And if that is what is the scenario, then if I replace your CE amplifier or your BJT with dynamic circuit or AC circuit or AC equivalent circuit, which was basically exact model which we used, now I'm going to use simplified model. Okay, if I use simplified model, therefore this is nothing but what? This is nothing but a simplified model. If I use simplified model, okay, this is your HIE, don't write, okay, and this is HFE into the input current IB. Okay, then this is what is your collector, this is your emitter, this is your base, this is your emitter, because this is common emitter amplifier. Okay, now this is what it is. Now we need to apply the voltage. This is Vs, right, and actually this is ground, anything is fine. This is Vs and this is RS. Okay, now this is what is your input voltage, Vi, basically this is VBE instead of saying Vi. Okay, that's fine, Vi with respect to amplifier parameter, and the current which is entering into your base is nothing but your base current IB, and the current which is entering into collector is nothing but your IC, and load is connected in between. This is your RL and this is nothing but your output voltage V0, and the current which is what is entering, right, the current which is entering into the load is nothing but your IL, which is exactly opposite to IC, because with respect to the transistor, base current is the one which is entering into base, collector current is the one which is entering into the collector. This is basically emitter, the current is nothing but IB plus IC, that is what is your emitter current, but not required because my input current is IB, output current is IC, emitter current is internal to your BJT, which we are not interested for common emitter configuration. Okay, we are not interested, that doesn't mean that IE is 0, no, we are not interested, we are not looking into it. Okay, therefore this is what your load and this is what your output voltage, therefore this is what your output voltage, let us say V0. Okay, and now it is defined with input impedance, right, the impedance seen into input port of your amplifier and defined with output impedance. The definitions won't change, remember. But now earlier exact model, now it is simplified model. Okay. Now if you have this, this is what is your model. Okay, simplified model. Using this we need to calculate. Okay. Now maybe I can give you the table. This is nothing but exact, using exact model AC parameter and using simplified model AC parameter. Simplified model AC parameter. Okay. Don't write, just listen here. Okay. When you go for simplified model, provided the load RL less than or equal to 4K or 5K, in the order of 4K. Okay. Now, what is the first one? Serial number. Okay. The first one, AC parameter. Here only you can take it. Okay. That's fine. The first one, current gain. What is current gain? We already calculated, right? What is that? Minus HFE divided by 1 plus HOE into RL, which we already calculated, right, before, but applying for common emitter configuration. Similarly, simplified model. What is current gain? I told, right? When I say simplified model, RL less than or equal to 4K, then what you do from here to here, we will neglect what? We will take HOE 0 and HRE also 0. This is what we are going to consider. Okay. If RL is less than or equal to this, now this is what we are going to apply. Therefore, it is simple or straightforward. Tell me if HOE is 0, because when I say simplified model, HOE is equal to 0. When HOE is 0, AI is minus HFE. Very simple, right? I can directly give you the simplified model AC parameters, but I don't want to give, I want to explain from always from circuit that will give you some, what they call, internal understanding of the circuit also. Okay. Now coming back to the circuit where we use the simplified model. What is the definition? From the definition let me derive. Okay, we'll come back to this only, but okay, this is nothing but the load current, the current which is what is entering into load, and the current which is what is entering into your amplifier. That is the definition, right? But applying to common emitter amplifier, the current which is what is entering into the load, IL, the current which is what is entering into your amplifier, IB, right? Therefore, with respect to this is IB and this is what is your IC. Okay, and this is nothing but minus IC. Both are same. Both are same. Okay. Now, and here emitter is, maybe this is what people say. Maybe you can say this is what is your emitter, and this is what is your base, and this is what is your collector. Okay, that is fine. Therefore, now what is IL? Basically, IL is nothing but minus IC. IL is equal to minus IC divided by IB. Tell me from simplified model, what is your IC? The current is entering into your transistor. Therefore, what is internal parameter? IC is in series current is constant. What is IC? HFE into IB. Therefore, if you put it minus HFE into IB divided by IB. IB will be cancelled. This is simply minus HFE. Therefore, what is current gain? Minus HFE. From the definition also, using simplified model equivalent circuit. If you don't want to do all those things, if you want very simple, if you are following only mathematical analysis, just take HOE 0. If HOE is 0, minus HRE. Done. Because simplified model is nothing but HOE 0, HRE 0. Okay. Now, let me continue in the same way. Therefore, second one. What is your input impedance? Don't write, just listen here. HIE plus AI into HRE into RL. Right, that is what your input impedance. Now let's see what is input impedance here. Therefore, what is RI? RI is equal to what? Definition. Actually from this, what is HRE? HRE is 0, then simply HIE. But let's see from the definition. What is the definition? The impedance seen from the input port, right? The impedance seen from the input port, because it is feed forward, therefore only input voltage comma input current. That's it. Therefore, the input seen from the input port is nothing but what? VI divided by IB, which is nothing but This is what is our resistance which we are seeing directly. Therefore, I can say, which is nothing but the definition, the input voltage Vi divided by Ib, right? What is Vi? That's input voltage KVL or Ohm's law. Ib into HIE. Therefore, HIE into Ib divided by Ib. Ib is cancelled. Therefore, yeah, this is nothing but HIE. Yeah, that is expected from this also. Okay. I am not treating them as formulae. Remember, derived formulae. Okay, from original formula, from exact model. Third one, voltage gain. What is voltage gain? Voltage gain is equal to AI into RL divided by RI. Okay. Now, what is voltage gain? Maybe you can substitute here, but let's see. Therefore, what is AV? AV is equal to definition. Definition is nothing but your output voltage divided by input voltage. Okay, your amplifier core voltage gain. I am not saying V0 by Vs. Okay, V0 by Vi only. I think this is the time to explain a point. Why we are not always speaking about V0 by Vs? Why we are always speaking about V0 by Vi? Because this is what your amplifier core gain. Why? Because when you insert buffer amplifier in between, then there is no impact of RF, right? If there is no impact of RF, then Vi is nothing but Vs, right? Then whatever you are calculating V0 by Vi, almost V0 by Vs you are getting. Therefore, anyway you are going to take out the impact of RF. That is the reason why we are only interested for amplifier core gain, because that is what we can get by inserting buffer amplifiers. That is what we have seen. That is the reason why we are looking for only V0 by Vi. Even though the real voltage gain is nothing but V0 by Vs, because your Vi will be equal to Vs, that is the reason why we always look for V0 by Vi. Okay, that is fine. I hope this is clear. That's fine. Now, definition V0 by Vi. This is nothing but V0 by Vi. Then what is your V0? V0 is nothing but IL into RL. This is nothing but IL into RL. Then what is Vi? Your Vi is equal to, because we already represented effectively the input impedance, right? What is Ri? What is Ri? Vi divided by Ib, right? Same thing here. Therefore, Vi is nothing but Ib into Ri. Therefore, what is IL divided by Ib? IL divided by Ib is nothing but AI. I think we got the same formula, which is nothing but AI into RL divided by Ri. This is what we got it, right? Same, but here we can substitute. Here we left it as it is, right? That time we left as it is because these are all bigger expressions which we need to substitute, therefore it will become bigger. Instead of that we left it like that, but I told that if you want to calculate AV, we need to calculate AI first and then RI, then AV. But here each is having only single term expression that you can substitute and then we can get it. Therefore, what is AV? If you substitute, what is AI? Minus HFE. And what is our load? RL divided by what is RI? HIE. Therefore, what is your voltage gain? AV is equal to minus HFE into RL divided by HIE, or minus HFE by HIE into RL. That is what is your voltage gain. Okay, fine. Now the last one, sorry, fourth one. What is R0? R0 is equal to 1 by Y0, right? Therefore, what is Y0? What is Y0? Y0 is nothing but HOE minus HRE into HFE divided by RS plus HIE, right? Now, can anyone tell? Don't substitute. If you substitute, you'll get the answer. But without substitution, can anyone tell from the circuit what is output impedance? What is your output impedance? R0. If you substitute also, you'll get it, right? When you take HOE 0, HRE 0, you'll get it. But from the circuit I want, okay? Because we need to use definition. What is the definition of R0? Exclude the load and the impedance seen from output port when Vs is equal to 0, right? Therefore, when you exclude the load, the impedance seen from output port when Vs is equal to 0. Tell me when Vs is 0, Vi 0. When Vi is 0, IB 0. When IB is 0, HSE into IB 0, it is open circuit. Therefore, what is output impedance? Open circuit. Open circuit is nothing but what? Infinity. Therefore, what is your R0? That is infinity. If you want, you can check from here also. If you want to go from here to here, HO is 0, HR is 0. HO is 0, HR is 0. 0 minus 0, 0. Y0 is 0. 1 by 0, infinity. That is fine. Okay? Take it. These are all derived formulae are your common emitter amplifier AC parameters using simplified model. Right? Take it. But out of 4, the main parameter which I am looking for, because ultimately my practical amplifier is nothing but voltage amplifier, I am looking for voltage gain. I am not looking for Ri, I am not looking for R0, because whatever Ri, whatever R0 you want, we can get it using CC amplifier or CB amplifier. No need to bother about impedance matching, right? Only we need to bother about power gain, ultimately the voltage gain in terms of, I can say, voltage gain we are looking from voltage amplifier, but it has to support power gain also. Okay? Therefore, this is what we are looking for. You can take this. Let me give you 2 more minutes to complete. Try to make it fast. You may ask what is it next, right? Next is nothing but, till now we have seen only like AC parameters, voltage gain, current gain, input impedance and output impedance, right? Now after all these things we have the conclusion saying that the default amplifier is common emitter amplifier. That is good, and no need to bother about Ri and R0 because they are important. The meaning of not considering Ri R0 from the given common emitter amplifier is nothing but we can achieve using common collector amplifier both at input and output for voltage amplification, and we are looking only for voltage gain. Okay? Yeah. Therefore, whatever, let us say we are designing audio amplifier, when you design audio amplifier using common emitter configuration, definitely we need common emitter configuration only, remember, because that is what is giving power gain. Therefore, then what is voltage gain we are getting? Yes, maybe you can calculate what is voltage gain, and you may say that this is what is my voltage gain. Remember, when you connect loudspeaker, your load won't be in the order of 10k and all. Okay, the impedance will be less than 10k, that is for sure. Then you can go ahead simply with simplified model. 90% of the problems from GATE examination, right, related to simplified model only. Okay, even though we studied the exact model, that is for study purpose, and but with respect to GATE examination perspective, therefore we always use simplified model voltage gain. Therefore, let me use default the simplified model voltage gain, which is nothing but minus HFE into RL divided by HIE. Now the next part is whatever audio amplifier you designed with a gain of something, right, considering H parameters and the load, that should be stable, right, means that should be constant. Whatever you designed, that should be constant. Due to some reason, if the gain is changing, not intentional change, due to some parameter which is what is affecting your voltage gain, that is what, if it is changing, then what to do, right? That part or that portion I am going to explain. Then with that, if I explain that part, that will lead to another circuit from common emitter amplifier, and that is what people try to use if you want to improve the variation in the gain. That part we are going to see. With that, I can say almost 90% BJT small signal AC analysis is done. Okay. Hope over. Okay. Now write down the next continuation part under simplified model is nothing but voltage gain stability. Write down voltage gain stability. The heading is voltage gain stability. Voltage gain stability. Okay. Heading is gain stability. By default, gain means voltage gain. Gain stability. Okay. If you know that, therefore we know that what is our voltage gain just now we got, right? What is that? Minus HFE into RL divided by HIE, right? Can I say your voltage gain is function of H parameters? It is function of H parameters, right? And remember, H parameters in turn depending on, therefore H parameters vary with respect to number one, temperature. What do you mean by temperature? The heat energy which is what is surrounded by the circuit. Number two, replacement. What do you mean by replacement? Let us suppose we designed an audio amplifier and due to some reason the transistor has burnt. Then what to do? We will take the circuit, right, the audio amplifier circuit to a repair shop. Then what he will do, let us say he found the issue saying that the transistor has burnt. Then what to do? Take out the transistor, throw it away, and then take the similar series or the same series, then put it and then come out. Now Because we know that no two transistors will have same H parameters. No two transistors will have same H parameters. It is something like Pauli's exclusion principle. When you take the Bohr model where there is a, if you take atomic model where we have nucleus and the electrons which are revolving around the nucleus, right? Then orbit 1, orbit 2, orbit 3, etc. No two electrons, even though maybe not orbit 1, orbit 2, in the same orbit, in the same suborbital, let us say s orbital or p orbital or d orbital or f orbital, in the same suborbital, even though same electrons, not same, two electrons are there in s orbital, those two electrons will not have same energy. Therefore, according to Pauli's exclusion principle, no two electrons have same energy. No two transistors will have same H parameters. That is the important point. No two transistors will have same H parameters. What is the reason? I am not explaining why no two electrons have the same energy. For that we need to have Bohr model, different concepts. We need quantum mechanics to explain that part, but I am not going to those details, which is not scope of our subject. Now let us say this is what your H parameter model. I can explain little bit why H parameters are depending on temperature, and why they vary with respect to replacement, or why two transistors will have different H parameters. Okay, maybe for that we need device operation. Okay, but I can say one thing, why they are not having same H parameters. Basically your H parameters depend on the geometry of your BJT, geometry in the sense the sizes, and they also depend on process. I can say doping concentration. We know that this is N plus P minus, and this is emitter, this is base, this is collector, and I told this is what is emitter doping concentration Ne, and base doping concentration Nb, collector doping concentration Nc, right? The beta are H parameters, right? Therefore, when I say I want the same structure or same base width, same emitter doping concentration, same base doping concentration, same collector doping concentration for all the transistors. Let us say I want identical transistors, right? That is what is my requirement as a designer. But remember, because of fabrication variations, right, you will not see same doping concentration for the same from identical transistors. Let me tell you the reason. Not only doping concentration, the base width is very important to define your HFE, that is basically beta. Therefore, the base width is very important. The base width itself will vary plus or minus some error, WB plus or minus some delta. Let us say this is what is my width of the base, which is physical width, WB. Then I want the same WB for identical transistors, but you will not get same WB, you will get some plus or minus delta. Let us say WB is 50 nanometer plus or minus something. Let us say plus or minus 2 nanometer, plus or minus 3 nanometer. That depends on the fab. Okay. Now, when I say WB plus or minus delta, then if width is different, then your HFE will be different. Okay. Therefore, why there is a variation? Why can't we get, when I say WB 50 nanometer, why can't we get 50 nanometer for all the transistors or for all identical transistors? Then let me ask you, because there is a natural phenomena, let me ask you another question that itself is the answer. Let us say in the classroom there are 50 students. If 50 students are there in the classroom, I am giving one specification. What is that? I am asking you to take scale and then pen. Then on white paper, I am asking you to draw exactly 10 centimeters. I am giving the same work to everyone. Everybody is trying to draw 10 centimeters, 10 centimeters, 10 centimeters. Therefore, spec is ideal. I am expecting 10 centimeters from everyone who are all there in the classroom. Now, if I collect all the papers from everyone, then if I measure using like very accurate scale, then surely everybody will not draw the same length, which is 10 centimeters. Why? Few people will draw 10 centimeter, few people will draw 10 centimeter plus some 2 millimeter, few people will draw 10 centimeter minus some 3 millimeter. Therefore, if I collect all like the lengths which are drawn, then all will not have same 10 centimeter. That is natural phenomena, right? Now, what is the reason? Natural phenomena. What do you mean by natural phenomena? Because people will start at a point, when you start at a point, when you draw, with what velocity you are starting and then with what velocity you are stopping, maybe you may extend little bit 1 millimeter or 2 millimeter. That depends on the velocity what you follow. Different people follow different velocity. Now coming back to fabrication, why we are having variation? Remember, people use mask. People use mask. For example, this is what is my width of the base. There I want to dope because I want p-type material. I want to dope acceptor impurities. In what portion you dope acceptor impurities, that is nothing but your width of the base, right? If there is a mask, which is what is, therefore we want identical transistors having same WB. What is the guarantee that whatever mask which is what is designed, which is having WB for all the transistors, what is the guarantee that the same WB is present? It is what is there from the mask. Yes, it will have some variation. You yourself is not able to draw 10 centimeter accurately, then when you are dealing with 50 nanometer, 100 nanometer and all, which is very small, definitely there is an error. That is what is called Prof's variation with respect to the geometry. And definitely the doping concentration also will have some error. Therefore, not only WB, your doping concentration in the base also plus or minus some delta, there will be some variation. All these things will give you the variation in the H parameters. If there is a variation in the H parameters, remember that when you replace the transistor, that transistor will have different H parameter than different voltage gain. Therefore, ultimately, your voltage gain is depending on H parameters. H parameters are depending on temperature. Surely, temperature will change. For example, if transistor is not burnt, then you will not replace. If you don't replace, whatever transistor you are having, those H parameters will be same. But remember, that is not dangerous, I can say, consideration. The dangerous one is nothing but temperature, which is what is there continuously. The variation in the temperature can be expected. If temperature is varying, then H parameters change. When H parameters are changing, your voltage gain will be changed. And there is another dependence, not only temperature replacement, there is something called ACE. That is what is called time. What does it mean? Let us say you designed an audio amplifier. You designed an audio amplifier at a time t is equal to 0. You only designed it. And you calculated or you got the H parameters from the data sheet at a given temperature. Okay. Then assume that temperature is not changing. I'm just taking out the independent parameters to explain another independent parameter effect. Therefore, temperature is constant. I'm expecting H parameters value constant. Then you designed it today. Okay. We are getting some gain, some sound, some quality or some volume, whatever it may be. Now the same settings are given, but if you continue to play your audio amplifier, let us say after 3 years or after 4 years, right, whatever circuit you designed, whatever gain you got at a time t is equal to 0, the same gain or the same H parameters for the transistor will be sustained. Therefore, we will not see the same H parameters after some time. Your H parameters change with respect to time. That is what is called ACE. Again, why? Again, a small example, a small analogy. Why our ACE is changing? Means ACE is changing means time is progressing. Therefore, our ACE is changing. With respect to ACE, the quality of the body will change, right? Maybe change in the sense it will be improved or it will be degraded. I'm not speaking about those parts. I'm speaking about the change is there with respect to time, right? Why there is a change? Natural phenomena. But I cannot say that natural phenomena can be observed, can be explained even for transistor. No, you will not agree. There should be a reason, technical reason or scientific reason to say that why it is changing with respect to time. Let me tell you. This is what your transistor. You connected the transistor and you biased the transistor in active region. Then there is a current which is what is flowing. Continuously are using from time t is equal to 0. Continuously the currents which are flowing through the transistor, right? Then remember, with respect to time, gradually the width of the base may change, or the impurity atoms, whatever you are having due to temperature and all, due to thermal agitation, right? What will happen? Maybe some of the impurity atoms may be diffused to next portion or next portion. Whatever it may be, the physical base width will be altered or changed. If the base width is changing due to time and the doping concentration effect is also changed, right, with respect to time, obviously H parameters change. Therefore, what I want to say, your H parameters vary with respect to temperature, with respect to replacement, with respect to age. Out of three, I can say age is also not very dangerous, because maybe after 3 years only you see the effect of gain variation, but not like today and tomorrow when you design the circuit now, up to 1 year, up to 6 months you will not see anything, therefore that is fine. Replacement, only when the transistor is burnt, then only you will go for replacement, else you will not go for replacement. Earlier people used to go for replacement. Nowadays who is going for replacement? If there is any issue, throw it, take new. That is what is the trend, which is what is going on, due to which the electronic waste is increasing, which we cannot reduce, but that is what everybody should think about it, and think about the electronic waste. If there is any issue, right, instead of thinking towards the new one, throwing the old one, right, maybe the trend is going like that, right, and then people are not releasing spare parts or spare transistors. And not only that, people can release spare parts or spare devices, but there should be someone to understand where exactly the issue. To understand where exactly the issue, we should know the circuit well. If circuit is simple, earlier circuits were like dealing with few transistors. Now because of VLSI, dealing with multiple transistors, then if circuit is complex, then finding out the issue is very difficult. Designer should come and then do it. That too with the investment of use time, debug time. That is very difficult. That is the reason why throw it instead of investing more time to debug and investing money to debug to give to an engineer. Throw it, get new one that is cheaper. That is what is going on. Therefore, now the trend is just replace instead of replacing. Throw the part, get the new sub part, install. Even though sub part is not available, throw completely part, then get the new one. That is what is going on, due to which the electronic waste is increasing. One side it is advantage, but another side that is a disadvantage. Okay, always for anything pros and cons will be there. We have to live with it, but recycling should be there. Okay, don't deviate the topic, but what it may be, this is what it is. Now they'll change, but that's what, with respect to time, okay, with respect to replacement that is also okay. But now temperature is the one which is what is the culprit, or I can say it changes continuously with respect to time. If you design the circuit at time t equals 0, yes, after 1 hour the temperature will be changing. Then definitely H parameters change. Then definitely your voltage gain changes. Therefore, because of all these things, I can say your voltage gain is not stable. I just explained the problem statement. Then to improve the stability, what to do? To improve the stability, what to do? That is the solution, right? Remember, if you understand the problem, maybe if you know the solutions, then you have to pick up one of the solutions based on the requirement. Requirement is the one which is what is going to drive to pick up one of the available solutions. For that, we should know first of all solution, then we have to go. But first of all, we should understand the problem. That is the first phase. Therefore, if you understand the problem is the voltage gain is not stable. That is varying. If you want voltage gain stability, what to do? That is the next step. You write it, then I'll explain and I'll give you the solution to improve the stability. Okay? Take it. I'll give you some 2 minutes, then I'll start. Is this over? Maybe you know this, but let me correlate with respect to system analysis. When I say with respect to age means what? Time. If time changes, the H parameters value changes, right? What do you mean by this? This is what we say time variant system, right? When you speak about signal systems or control systems, our assumption is the techniques whatever you are studying, Fourier series, Fourier transform and Laplace transform, discrete Fourier transform, FFT, right? Whatever techniques you are studying from signals and systems, right, or control systems, there is an assumption, right? What is that? System should be LTI. The system should be linear and system should be time invariant. But practically all the systems are non-linear. I'm going to explain that. After completing BJT small signal AC analysis, I'm going to explain that part and then going to explain the solution also. Okay? The name itself is having the solution, but you will understand that later on. Now, practically all the systems are non-linear. Practically all the systems are time variant. Example, with respect to time, your H parameters are changing, then your voltage gain will change. Therefore, the system parameter is changing with respect to time, means time variant system. Therefore, then what to do? Therefore, all the systems are non-linear. To make it linear, what to do? That part I'll explain. Give me some time. All the systems are time variant, right? Then to make time invariant, what to do? You know what is the solution people are going on, or people are following? Up to what time the parameters of your system are not changing, or even though they are changing, if they are meeting the spec, go ahead. After some time, if the parameters are changing and which is directly impacting the spec of the system, don't use the system. If you use the system, the designer who is designing that, or the production company which is what is giving or delivering that product, saying that we are not guaranteed. Therefore, that's something called guarantee. That's why whenever a chip or integrated circuit is designed, remember it will have some lifetime. It will have some lifetime. That doesn't mean that it will not work after some time. It will work, but it is not guaranteed that it will meet the specification. You will get it, but the performance will be degraded. But till some time, whatever they say, let us say 4 years. Till 4 years, it will work. What does it mean? Whatever specs which are specified, those will be met. Maybe after 4 years, the specs won't be met. Even if you want, you can continue. One of the simplest example to explain about the solution for time variant systems is your smartphone. Tell me, you are purchasing smartphone today. How long are you using a smartphone? Right? How long are you using your smartphone? We are not using smartphone lifelong, right? You are purchasing now. I can say hardly people use, I can say average, on average overall the world people got this number, which is real number, 4 years. That is the average number. Few people may use 5 years, 6 years. Few people may use only for 1 year and then change the phone. That we cannot guarantee. But on average, people are using it for 4 years. Then why to design a mobile processor which is so robust? What does it mean? Designing a mobile processor which will work for 20 years, but it is costly. Instead of that, don't bother about the performance after 4 years. Design it only for 4 years, where you will meet the spec for 4 years. After that, even though you are not meeting the spec, don't bother, right? Therefore, what is the solution for time variant systems? The system which is varying with respect to time, is nothing but use until that point, later on don't use it. Or even though if you use it, live with performance degradation. That is the reason why if you use your smartphone continuously, the performance will be degraded after some time. That is explained because of time effect, because of age effect. I hope this is clear. That is what people practically follow. Maybe if you take all mobile processors which people use throughout the world, typically I can say 4 years, and coming back to your desktop or laptops where you use your processor which is inside, people design it for, I can say 7 to 8 years, because we will not change your laptop continuously, right, for 4 years. Definitely you will use it for like at least 7 to 8 years. After that performance will be degraded, but that is fine, which is acceptable. But if you come to server market in the sense wherever you have data processing like Yahoo, Google, Facebook, right, wherever there is a processing, right, server means what? Data processing. Wherever you have data processing, which is like with huge memory, huge processing capacity and huge power consumption, right, then obviously it works continuously, then which are the servers are very costly. We cannot change for 4 years, we cannot change in 7 years until unless there is a strong requirement to improve the performance. Maybe typically people can use like for 10 years, 11 years, 12 years and all. Therefore for servers, people design the processors, very powerful processors which are kind of robust. They can work for like 10 years, 11 years, 12 years. Therefore after that you have to upgrade. If you don't upgrade, the performance will be degraded. You understand the point? Therefore, what is the solution for time variant systems? Till that point where the spec is met, right, use it. After that upgrade. That is what is the solution which we are following now. Therefore practically all the systems are non-linear, practically all the systems are time variant, but the solution for time variant systems is nothing but I already told, use till the specs met, then later on change or upgrade. Number 2, for linearity what to do? I'll explain that part later on, because all the systems are non-linear, because we use BJT, JFET, MOSFET or PN junction diode in the systems. Surely they are non-linear, therefore system is non-linear. To get linearity, what to do? Remember, if system is not linear, Fourier series, Fourier transform, Laplace transform, they are not valid. Therefore all those techniques are what all the principles what we derived, right? Remember, they are true only for LTI systems. And if you go for Fourier series or Fourier transform, LTI plus system should be initially relaxed. Okay, I'm not going into those details, but the system should be LTI, right? How to make linearity from non-linear circuit or system, that part I'll explain later on. Okay, for the time being, let me stop here, then we can continue in the next session about like how to improve the stability. Therefore, from this session what we got to know, the limitation of your existing amplifier, basically common emitter amplifier. Yes, we got the conclusion saying that it is providing very good voltage gain, but the problem is the gain is not stable. Wherever gain stability is important, remember in few applications gain stability is not that much important. If gain stability is not that much important, you can go ahead with the gain, even the gain variation is there, that is fine. Wherever gain stability is very important, remember, then we need stability. Then how to improve the stability, that part I will explain in the next session. Maybe we will continue after we will continue in the next session. Therefore let me stop. Okay, thank you.